Okay, welcome to EGR445 Mechanical Engineering Systems. In today's class, we are going to talk about design of screw jack. And we studied the basic concept of screw jack design. We looked at what we mean by power screw, what are the applications of power screw, and we designed some mechanical systems using power screw. Now, in today's class, I would like to work on a couple of interesting problems related to power screws. So first and foremost is design of a screw jack. So design of a screw jack. Screw jack is a very common system that is used for lifting the load or holding the load at a particular location. And if you look at a simple screw jack design, it will be something like this. We would have a central screw. So this is the screw, this is the power screw. It could be square threads, it could be Acme threads. So this is the screw. Then there is going to be a nut, and this nut is going to hold the screw in place. So there will be a nut. Nut will also have threads, same matching threads. And this nut will be either press fitted or attached somehow using a set screw or maybe some bolts to this housing. Usually the housing is made up with cast iron, and the main purpose of housing is to provide base and support. And there are different designs possible, but I just want to give you a very simple design. This is how the housing is going to look. Now, if you look at the nut, typically the nut has a head. So here, this is called as the head. So screw is attached to a head, and then usually there you would have some sort of a projection and some sort of another bolted joint, and you have a cup. Again, different designs, different variations are possible, but this is a very simple design that we are going to talk about. So if you look at the housing is rigid, usually made with cast iron. Then, so this is housing. This is nut. This is power screw. This is head. And usually you will have a handle that is attached to the head. So what happens is we rotate the head. As the head rotates, the nut, which is firmly attached to the head, rotates, and depending upon whether you rotate clockwise or counterclockwise, the cup and the load, so the load will be somewhere here. This is the load. Load will be raised. That is how a screw jack, a simple screw jack, works. Now, what we want to do is, we want to design the screw jack, means find the important dimensions of this screw jack assembly. And some dimensions are important, some dimensions are empirical, some dimensions are they are actually from manufacturing criterion. So for example, if you want to mold something or if you want to cast something, you need to have certain amount of clearance, you need to forge something, you need to form something, you need to have minimum certain wall thickness. So these criterions come in the picture when we actually take this assembly and start manufacturing. So what I'm going to do is, I'm going to indicate the important dimensions. So for the screw, there will be something called as the core diameter or the inner diameter. Then there is going to be an outer diameter, which is DO. Then you will have a diameter of the nut. So you are going to have a nut diameter, and I'm going to call that nut diameter D1. And then I could have an external diameter for the nut, and this is D2. Then I could have the length of the handle, so this is L. And then you could have other dimensions like thickness of the housing or the lifting height and so on and so forth. Now typically at the end of the nut there is some sort of limiter, and the reason for this limiter is you don't want a screw to go out of the nut. So which means if you raise the screw, the maximum lifting height will be constrained by this particular protrusion. And the reason for that is you want to lock the screw when it is raised to the maximum level. And one thing I just want to tell you that the nut could be press fitted, or sometimes you might see some sort of a screw that is holding the nut in place. So you could have some sort of a set screw. Now the design procedure is similar to the design of power screw. So what we will do is, we will design screw, design nut, design handle, and you can find out all other auxiliary dimension based on engineering principles. What I'm going to do is, I'm going to give you a recipe to find out the procedure for design. So the problem would go something like this. Problem: design a screw jack to lift a load W newtons. And at this point, they may give us the different materials. They will say nut is made up with alloy steel, or the screw is made up with some others alloy steel. The handle is made up with mild steel. The head is made up with some other material. So they could either specify the materials, or it could be just open-ended. So either they will give us the material, or we can select the material depending upon application. And clearly, we would be referring to design data book to find out different material properties. So we are going to start step by step. Step one. In step one, we will find the core diameter of the nut. And if you look at the core diameter of the nut failure is in pure compression. Now, please understand that this nut is held in place by a support at the bottom and is loaded on the top. So this load is purely compressive. So step one, determination of core diameter. Now, assuming the compressive strength of the material of the screw material is known, W divided by pi by 4 times dc square is going to give me dc, which is the core diameter of screw. And please note, this would be the same for the nut, because nut and screw, they have to be assembled. So they should have same core diameter, same outer diameter. Then they should have same pitch, same type of threads, and so on. Next step, step two. In step two, we have to find out the amount of torque that is needed to raise or lower the load. Now, as you know, there are two things that we need to consider here. First, we need to know what is the friction angle. So, what is the friction angle? And next thing we have to know what is the helix angle. Now, if you look at the design data book, and if you look at the screw jack design, they will specify the values, or they will give you the recommended values of friction angle depending upon the different materials in contact. Typically, the friction angle depends upon whether the nut and screw pair is lubricated, non-lubricated, what is the duty cycle. It could go anywhere from 0.1 to 0.3. Helix angle could go anywhere between 7 to 14 degrees. So again, that depends upon the design consideration. So we will have to refer the design data book and then find out the appropriate values of friction angle and helix angle. So determine torque. Now at this point, what I want to tell you is, once we know the value of DC, we can approximately find out the mean diameter. So if you look at the core diameter, and if you look at the outside diameter, usually core diameter is equal to 0.8 times outside diameter. So once we know the core diameter, we should be able to find out the outside diameter. Mean diameter is DC plus DO divided by 2. So once we know the mean diameter, we can use that information to find out the value of torque. So T is equal to torque needed to raise the load is W multiplied by dm by 2 tan phi plus alpha. And this is the exact same equation that we used in last class. Now, one thing what we want to talk about is first that this torque, and because of the simultaneous action of load, if you take a look at the power screw, if you look at a power screw, you have torque and you have direct load W. So because of that, you're gonna get normal stresses and you are gonna get shear stresses. Combined action of normal stresses and shear stresses give rise to principal stresses. And maximum shear stress. So anyways, we need to find out the value of sigma. Sigma will be calculated as W divided by pi by 4 dc square. A word of caution. Now, when you calculate dc from step 1, you are never gonna get a dc for core diameter that is perfectly rounded. So for an example, you may get core diameter 20.32. So to be honest with you, this 25.32, you won't be able to find a screw with this dimension. So this needs to be approximated to say 26 millimeter of core diameter. And you will use this 26 millimeter in here to find out the actual value of sigma. So clearly, actual value of sigma is going to be less than sigma c, because we went and we rounded the value of dc. Next thing is we need to find out the value of tau. Tau is equal to T divided by J multiplied by R. Now value of torque comes from equation 2. So value of torque comes from equation 2. Now J, if you look at the way we are going to solve this problem, it's a sort of a solid shaft. So I would use pi by 4 dc to the power 4 dc by 2, and sorry, pi by 32, and then from here I would get the value of tau. Now please note, I have two values. I have the value of sigma, I have value of tau. I can find out the principal stress. Sigma principal is equal to 1/2 sigma plus square root of sigma square plus 4 tau square. I can also find out tau max is equal to 1/2 square root of sigma square 4 tau square. And both these values should be less than the design strength of the material. In other words, if you choose alloy steel as the material for the screw, then sigma P needs to be less than sigma design of the screw, and tau max should be less than tau design for the screw. Any questions here? If you have a question, you are welcome to raise your hand or just type your question in the chat window. Now we want to proceed further and find out the values for the nut. So next step is step 3. Height of the nut height. Now there are various ways the height of the nut can be found out. You can find out the height of the nut because of the shear failure. You can find the height of the nut because of the bearing failure. You can find the height of the nut because of the crushing failure. So again, all these approaches are valid. So in this case, I just want to look at the failure of nut because of the bearing. Yes, this procedure is in the textbook, but it's a different chapter. The name of the chapter is power screws. So if you look at the nut height, sigma B is equal to the load W divided by, now I need to look at the area, which is pi by 4 d outside square minus dc square. This is one single area, and then you have n, which are nothing but the number of threads in contact. So please note, value of sigma B is nothing but the bearing value. So sigma B is the bearing strength. So value of W is known. Please note, the outside diameter of the nut and core diameter of the nut will be exactly same as the outside diameter of the screw and the core diameter of the screw. So what it means is this value is known, this value is known. They come from screw design. Step 1. So these values come from step 1. This sigma B value will be given to us. Value of W is also given to us. So the only unknown in this equation is N. And please note, we discussed in last class, for positive contact, N minimum should be 3. So in the case of screw jack, you can consider N minimum to be 3 or 4. So once this is known, once we know the number of threads in contact, say for particular screw design, you apply these equations and find out the value of N is equal to 1. So the screw may be safe in bearing, but one thread will not ensure proper engagement. So to make sure that the nut and screw are properly assembled, you need to have minimum 3 to 4 full threads in contact. So you can state at that point that minimum number of threads we are going to assume is say 4, and then you can actually proceed. And now to find out, so here in step 1, you already know the value of DC and DO. The pitch is approximately DO minus DC. So I need to explain this a little bit. So if you look at the screw is going to look like this. So the screw would look something like this. So it will have a core diameter. It will have an outside diameter. And then there will be something called as the pitch. This is the pitch. So from this point to this point. So depending upon the number of threads in contact, you can find out the height of nut. Is equal to N multiplied by P. And as we discussed, P is equal to pitch D outside minus core diameter. Now this is approximate. Many a times what you can do is once you find the core diameter, you can refer to the design data book, and the design data book or American Screw Manufacturer Association will list preferred numbers. So basically the preferred size of screws. So how do these preferred numbers come into existence? So the idea is over so many years or decades of using different mechanical components in different industries, these folks from industries, they come together and they kind of try to standardize the components that are used. And the advantage of standardization is then you can have interchangeability. One manufacturer can manufacture screws or parts for many subsystems. A subsystem assembler can assemble the subsystems. Those can be used by a lot of OEMs. So there is lot of cost saving with standardization. And with mass production and mass market, the price of a product is a very key parameter that everyone has to take care of or everyone has to look into. So from these discussions, they come up with preferred dimension, and the idea would be what dimensions would be good in this particular range. For an example, if you have a shaft design need, so what are the typical sizes of the shaft? Say if you want to design a shaft between say 10 millimeter to 30 millimeter. So what would be the dimension that would satisfy most of the customers? Would that be a shaft of 22 millimeter, or would that be a shaft of 25 millimeter? Would that be the shaft of 27 millimeter? And then what would be its implications on other components that get assembled with that shaft? For an example, what would be the bearing sizes? What would be the typical tolerances? What would be the type of fit? So all this analysis gets carried out, and this is not just one person's job. Over the period of time, probably decades, then these standards get developed, and then what you have is you have preferred numbers and preferred dimensions. So the idea is if you have a screw of a certain preferred dimension, most likely that screw will be in stock at the vendors like Granger, or maybe some other manufacturer in China, or manufactured in US, or manufactured in Mexico, would have that system built in or manufactured and in stock. So it's called a stock item or a catalog item. So advantage of using a catalog item is it's cheap, it's commercial off the shelf, and then you can use it in your design. So what you can do is, at this point, you can actually look at data book, design data book, and find out what are the preferred pitch dimension for that particular screw. So for an example, you will see that a 25 millimeter screw has 7 millimeter pitch, or a 25 millimeter screw can have 8 millimeter pitch or 10 millimeter pitch, depending upon the application. But as a rule of thumb, if the data book is not available, you can just approximate the value of pitch as the difference between the outside diameter and the inside diameter. Okay, the next step is, now we have to check the nut. So we talked about this failure in last class, but I just want to talk about it again just for clarification. So what I'm trying to show here is, I'm trying to show you an exaggerated view of screw and nut assembly. Okay, so this is the nut, and I want you to understand the nut is gonna look like this. So if you follow the purple shade, this is how the nut is gonna look like. And just visualize that this blue screw that sort of broaches out the nut. So what would happen is, the nut would actually shear off at these points. So this is where the shearing of threads could happen. And to compensate for that, we have to make sure that our design is safe. So shear stress to check for shear, tau is equal to W divided by pi times N times DC multiplied by the number of threads in contact. Now, to find out the number of threads in contact, what I want you to do is, I want you to visualize the pitch. So for a second, when you look at the pitch from here to here, this is the pitch. So the thickness of the thread, T is equal to thickness of thread is equal to P divided by 2. I want you to look at just the picture that I have drawn over here. And if you see, it is something like this. So when you are looking at the pitch, which is from here to here, the T dimension is this. This T is equal to P by 2. This is P. And with this, you can check if the screw is safe or not. And if it is not, you have a choice. You can go back and increase the number of threads. Now, you will notice that for nut and screw, typically, if they are made up with the same material, you can just consider the value of DC and you would be okay. But sometimes if the nut is made up with a different material, it might be a good idea to check the screw for the shear failure and the nut for the shear failure as well. So what I'm trying to say here is there is a possibility that nut could fail, or there is a possibility that the screw could fail. And if nut and screw, they are made up of same material, then that question does not arise. But if they are made up with different material, you might want to check if the nut is safe and the screw is safe. So assuming everything checks out, everything is safe, we can move on to step 4. In step 4, what I'm going to do is I'm going to find out the diameter of the nut collar. Now, if you ask me what is the diameter of the nut collar, so what I want you to do is look at the dimension B1. So I'm interested in finding out the diameter of the nut collar. And that diameter is found out considering the tearing or the tensile failure of the nut. So sigma T is equal to W divided by pi by 4 D outside, which is D1 square, minus the diameter of the nut DO. And in this equation, W is given to us, this is sigma T. D0 we already know, and the only unknown from this equation is D1. Then next step is find the outer diameter, which is D2. And I want to show you this outer diameter. If you look at the outer diameter, this outer diameter D2, it's sitting on the housing. So the failure of the outer diameter is because of the crushing or compression failure. So you will use sigma C is equal to W divided by pi by 4 D2 square minus D1 square. And then from here, we can find out the value of D2. Now, the last but not least is the thickness of the nut. And this is the thickness. So I'm going to call this T1. And if you look at the failure of the nut thickness T1, that is due to circumferential shear. So thickness T1 is tau W pi. Now, if you look at the diameter here is D1. So this is the diameter. This is the diameter. D1, D1. Now here, D1 we already know. The value of W is given to us. So with this, I should be able to find out value of D1. Now these are the main important dimensions of the nut. Just let me show you what these dimensions are on the actual nut. that would kind of make sense. So our nut is something like this, and that fits into the housing here. So where is this housing? And then this is the center line of the nut, and then this is the core diameter and the outside diameter. So you have this dimension as D2, this dimension as D1, and this dimension as D1. So we have designed the screw, we have designed the nut. Now what we want to do is we want to find out the other auxiliary dimensions, which is, for example, the diameter of the head, so and this diameter of the head is, say, D3, is anywhere between 1.5 to 3 times DO. So if you look at the head, clearly the head has to sit on top of the screw, but it should not be greater, or the dimension should not be too big so that it extends the outside diameter of the nut. So it should not be greater than D2, but it should be, so this dimension is D3. And then usually if you want to look at the diameter of the pin, so D pin, this is the diameter of the pin. Is usually D3 divided by 4. Again, this is an approximate dimension, and the variation in this dimension are possible. And then what we need to do is we need to find out the length of the handle. Then we need to find out how much torque it's gonna need, assuming there is some sort of bearing surface. And what I'm gonna do is I'm just gonna give you a very simple equation for the bearing. So let me draw the figure once again. So now we are looking at the top section. So this is the head, this is the nut, here is the nut. So let me show you the nut here. This is the nut. Usually here there is going to be a plate. Here there is going to be a plate. And the purpose of this plate is to sort of minimize friction and then minimize the unnecessary wear and tear on the nut or on the screw, so that they don't go out of alignment. So there are 2 or 3 ways this plate can be designed. And the easiest way, the way we can do it is we assume the dimension of the plate equal to the dimension of the head. So we assume dimension of the plate is equal to dimension of the head. And then this is going to give us additional friction. So we will assume uniform wear criteria So how is this criteria applied? So what I want to do is I want to show you the three-dimensional view of this plate. If you look at this plate is something like this. And what's going to happen is there is going to be vertical load everywhere on the surface of this plate. So there is going to be vertical load on the surface of the plate. And imagine for a second that once we rotate the handle, the relative contacting surface between the plate and the head is going to start moving. So you have this handle, this is the head, and if you rotate the handle, the head would rotate. What that means is you are going to have the frictional force which is perpendicular to this normal force along the surface. So if you look at from the top view, you're going to have these frictional forces all on the surface. And if you take the average frictional force and you multiply that by the average lever arm, if you take the average frictional force and if you take by the average lever arm, you can approximately find out the amount of frictional torque that you need to overcome. Now, what is the average lever arm? So if this is R inside, R1, if this is R outside, RO, RI, RO, RM is equal to RI plus RO divided by 2. If the coefficient of friction is given, you can assume the coefficient of friction anywhere between 0.1 to 0.3. You can find out frictional torque is equal to 1/2 mu W Ri plus Ro. Now, assuming the plate dimension is same as the head dimension, assuming the plate dimension is same as the head dimension, Ro is going to be dO by 2 and Ri is going to be d3 by 2. And please note, value of dO is known from step 1 and value of d3 is known from step 4. So d3 will come from here. And that will give you the frictional torque. The value of W is already given to us. So we are designing the screw jack for certain value of W. Now, once we know the friction torque, we can find out the value of total torque. So step 5, which is handle design. Total torque is equal to T load. Please note, this T load comes from step 2. This is from step 2 plus T friction, that comes from step 4. And that gives you the total torque. Now, at this point, what we need to do is we need to see how is this screw jack gonna get operated. The most common way a screw jack is operated by a human operator. So if you look at the humans, human can apply 300 to 400 newtons of force by hand. Force by hand. So what you can do is you can divide this total torque divided by say 400 newtons, and that will give you the length in meters. So this will give you length of the handle in meters. Now sometimes you want to find out the size or the dimension of the handle. So let's look at the handle design. You have this head, and then there is this handle. I'm going to use a circular handle, and from the previous step we found out the length of the handle. So this length is known. Now what I want to do is I want to find out the diameter of the handle. So what is the diameter? And this can be done using simple bending. I will assuming cantilever support, the bending moment, and this is the maximum bending moment, is force multiplied by length, which is nothing but amount of torque, amount of total torque that needs to be applied. And then I can use the equation sigma is equal to Bm max divided by I multiplied by Y. If D is the diameter of handle, I'm gonna call DH. Sigma is equal to Bm max DH to the power 4 by 64 multiplied by pi DH divided by 2. This value comes from the data book. And depending upon the handle, you can use a cast iron handle, you can use a mild steel handle, or you can use a rebar. But with that, you should be able to find out the diameter of the handle. Now, many a times, what happens is that you will notice that the power requirement or the amount of torque requirement is very, very high. So in certain cases, you will notice the torque requirement is high and your handle maybe comes around 2 meters. So in that case, rather than extending handle only on one side, you could have a potential solution, something like the handle is going through the head. So this is the head, and you could have a handle that is going through the head. And rather than one person lifting it, you could have 2 people. So you could have one person pushing from here, and you can have one person pushing from here, and they will work together to raise the load. In certain cases, you will notice that the torque requirement are super high. So in that case, what I have seen happening is you actually attach this to a transmission. So you have the head. This head is somehow attached to a transmission, either using some sort of drive, gears, some sort of power transmission system, and then you could have a gear assembly, and then you can have a motor that actually rotates this system. And with that, there are some additional complications that could happen. The design is no longer very straightforward, and you have to make sure that the motor remains stationary, but still the screw can be raised, and there are other aspects. So you could have a transmission, so you could have a manual operation, or you could have a transmission plus motor. So this is how the screw jack can be designed. And please note, these are some of the simple steps. The last thing that you might want to check is you can check for the buckling. And usually screw jacks are safe for buckling because we don't raise the load to a very high, the height is limited. But if you like, the last step, you can check screw for buckling. And with that, you can design the screw jack. Now, at this point, I want to ask you if there are any questions. Are there any questions on the screw jack? If you look at the textbook, there are a couple of worked out problems in the textbook, and you are welcome to look at or refer those problems as reference, but the design procedure is fairly straightforward. Any questions here? Okay, if there are no questions, I want to discuss a variant of a screw jack, which is called as a toggle jack. And I don't, if you have changed the tires, most likely you have had used this toggle jack. So how does a toggle jack look like? The biggest advantage of toggle jack is it can be stored in a very compact fashion. So design of toggle jack. So in toggle jack, unlike screw being vertical in screw jack, the screw is actually horizontal. And just like turnbuckle, it has left hand and right hand threads on the either side. So on one side, it has left hand threads, and on the other side, it has right hand threads. And then there will be a nut. There will be a nut. And please note, if you have a left hand screw, you will need a left hand nut. If you have a right hand screw, you will need a right hand nut. So you have appropriate nuts on the left and as well as on the right hand side. And then you have a support plate here. and then you have a base, and if you want to raise or lower, what you do is you apply the rotation or you apply the torque at the end. And usually there are limit stops here, there are limit stops here. And if you look at your vehicle or car, you will usually have a simple toggle jack uh, that can be used to raise your vehicle in case if you want to change the tires. So everybody understood the toggle jack design. So you have, say, left hand screws and right hand screws. So you have, say, this is left hand thread, this is right hand thread. So one thing that is important is screw is horizontal and the nut, there are two nuts actually, nut is vertical, and the load that is going to be supported is over here. Now if you look at the way this configuration is, the load W is not directly acting on the screw. So here is an observation. So the first observation is screw horizontal, nut vertical. And the second observation is load W is not directly applied. So if you look at the free body diagram, what you have is you have W. That W is distributed over here. That W is supported by two members over here. So this W is supported by these two members here. And then a component of force supported by the nut. So I want you to understand what is happening. This is the load W. This load W is acting on this component. This is the load bearing member, or this is the load plate. This is the load plate. Now this load plate takes that entire load, and this load plate is supported by two links. This is link 1 and link 2. So this is force in link 1. This is force in link 2. Now one thing that I want you to observe, that the angle, this angle theta changes. So this angle theta changes depending upon whether the jack is lowered or raised. So in other words, if the load plate is down, all the way down, the load plate is all the way down, then you're gonna have something like this configuration. So if the load plate is down, then you're gonna have configuration like this. I'm gonna call this theta minimum. If load plate is all the way up, then you're gonna have configuration like this. I'm gonna call this theta max. So which means even though W is remaining same, since the relative angle between these links is changing, the actual load on the screw is changing. So please note, as theta changes, the load on nut and screw changes. But what we are interested in finding out the maximum value of load. So the question is, what is the maximum load on nut plus screw assembly? Because if we design the nut and screw assembly for the maximum load, then it should be able to take the minimum load. So, and the way this is done is, it is done using a simple static equilibrium. And what I'm going to do is, I'm going to show you that how the static equilibrium can be carried out. So let's look at the load plate. The load plate load W will be shared by these two guys, W by 2 and W by 2. Then what you'll have is, you're gonna have the force in link 1, and let's assume at this angle is theta, this is 90 degrees, this is 90 minus theta. So applying summation of forces in y direction is equal to 0 minus W by 2 plus FL1 cosine of 90 minus theta is equal to 0. That gives me FL1. If you look at cosine of 90 minus theta is nothing but sine theta. So this equation becomes W by 2 sine theta. Now let's look at the force in the screw. This is our force in the nut, Fn. Summation of forces in the x direction is equal to 0. So 0 is equal to FL1 cosine theta minus Fn. So Fn is equal to FL cosine theta, FL1 cosine theta. And FL1 is already known, which is W by 2 sine theta multiplied by cosine theta. So this equation is W by 2 tan theta is equal to Fn. So if you look at the load in the nut, Fn is equal to W by 2 1 divided by tan theta. Now what we need to do is, please understand, we have to find out the maximum value of Fn. To find max Fn, so Fn will be maximum when tan theta will be minimum, and tan theta will be minimum when theta is going to be minimum, and theta is going to be minimum when the jack is at the lower state. So when lower, theta is going to be minimum. So the first step is, when you are trying to design the toggle jack, you will look at the toggle jack design. The question will be something like this: design a toggle jack for load W, and then they will specify some geometry constraint. So they will say the uh, the toggle jack needs to raise the load by a certain amount, but the geometry of the toggle jack should be in between, say, 150 millimeters to 200 millimeters, and so on and so forth. So geometrical properties will be given to you, or they will give you the values of theta directly. So based on the values of theta, or based on the geometry, you can find out the value of theta and find out the maximum Fn. And once max Fn is known, the procedure to design the toggle jack is exactly same as design of screw jack. So what you can do is, once you find out the value of load in the nut, then you can actually design the screw. So you can follow the same procedure. Once you know maximum Fn, once you know the material, you can design the screw, can design nut, and then you can design the levers. And this is how the toggle jack can be designed. Again, the procedure for toggle jack is exactly as screw jack. There are a couple of examples that are worked out in the textbook. I would encourage you to take a look at those examples and then follow them through. Okay. Any questions on the screw jack or the toggle jack design so far? If there are no questions, we'll stop here for the screw jack design, and we can start the next chapter, which is design of springs. It's almost 7:15, so I'm gonna give you all a break of 15 minutes, and we'll be back at 7:30, and then I will discuss the design of springs. If you have any questions, you are welcome to raise your hand or type your question in the chat window. So the next chapter that we are going to study is design of springs. And if you look at springs, there are very many designs. So you can have a helical spring. So the helical spring would look something like this. It could be closed coil or it could be open coiled. So there is something called as the closed coil, and there is open coil. So in the closed coil springs, the angle of helix is usually less than 10 degrees. So helix angle is less than 10 degrees. In the open coil, helix angle is greater than 10 degrees. The next type of spring is the spiral spring. So if you look at the spring, it is like this. If you had old mechanical clocks or watches, they use spiral springs a lot. Spiral springs are applying torque. So helical springs usually apply forces. Spiral springs can apply torque. Then you could have a leaf spring. And if you look at the leaf spring, these are the springs that are used in locomotives or trucks. If you look at, and then there is a center bolt, and then there is rebound clip. So you have leaf spring. And the last but not least is Belleville spring. And these are like sort of a bellows or sort of air springs. Probably you have seen the cars with adjustable suspensions, or you might have seen cars with air springs or trucks with air springs. So you have the springs that are a little bit different shaped. Now, what are the typical applications of springs? So springs are used in a lot of application. First, they can be used to store energy. To exert force. To absorb shocks. They can be used in instruments to measure forces. For an example, spring scale. And 5, to change vibration characteristics. Now the springs can be used in tension or springs can be used in compression. So there are tension springs and there are compression springs. And as the word suggests, tension springs are used to apply tension and compression springs are used to apply compression. For an example, if I want to show you a tension spring is gonna be like this. So what you do is, this spring is going to apply forces in this direction. If you have a compression spring, then you will have a spring like this. that spring will be applying compressive forces. So you could have tension springs, you could have compression springs. Some important definitions for the spring. The first and foremost is something called as the spring rate or stiffness. Also known as stiffness. This is load per unit deflection. So if you have force and if you have deflection, then the slope of this is called as spring rate, which is force by deflection. And you could have a linear spring where the relationship between force and deflection is a straight line. You could have a nonlinear spring. And nonlinear spring, you will see two types of springs. One is a soft spring and the hard spring. So in the case of soft spring, as the deflection increases, the spring starts becoming softer, which means the amount of force that spring exerts as the deflection increases is less. Or you could have a hard spring. What it means is, as the deflection, if you start increasing, it is harder to deflect the spring. So it's difficult to compress it after certain limit. So there is a soft spring and there is a hard spring. The unit of spring rate is usually Newton per meter. So that is the first important parameter. The second important parameter is spring index. Spring index is the ratio of the coil diameter by wire diameter. And this may need a little bit of explanation. So what I'm going to show here is I'm going to show you a slightly exaggerated view of a spring. I'm going to show you a slightly exaggerated view of the spring. And you will notice that the spring is sort of the coiled and it has a wire that is actually coiled. So, and at the end, you are going to have, it is something like this. So, it is like this. This is the center line. And this is the center line of the wire. If you look at the wire, this is the wire. This is the wire diameter. And this diameter is the coil diameter D. Now, if you look at this angle is called as the helix angle. And this spring is actually a big helix. The next thing is the free length. So that means what is the free length of the spring when it is not loaded. So for an example, in this particular case, this spring is not loaded. So that is the free length. So this is the free length. Now, when you apply the load, so after applying load, you have solid length, which is after applying load, spring gets compact. So this is the load. And the next thing is the pitch. So pitch is the difference from here to here. This is the pitch. Now, what I want you to think about is if you apply the load on the spring, and the spring is something like this. So if you apply the load on the spring, so this is the load, the spring gets loaded in direct shear, and the spring is also loaded in torsional shear. So let's for example, let's look at the amount of the loads that are coming. So consider that there is this external load P, and this load P is acting at the radius. This radius is d by 2. So this is the radius at which P is acting. The other thing is, if you have this external load P, this load P is also directly acting on this cross-sectional area. So this P is going to give you a direct shear stress, and it's going to give you torsional shear stress. So what we need to do is we have to make sure that the spring that we are going to design is safe when these two stresses are simultaneously acting. So let's derive the stresses that are acting on the spring. So shear stress in spring, I'm going to call that as tau S, which is the total shear, which is equal to direct shear plus torsional shear. So direct shear is W divided by pi by 4 d square. And please note, small d is the wire diameter, plus torsional shear is T divided by J multiplied by R. So this becomes pi by 4 d square, plus this becomes W, which is the load, R, which is the radius, then pi d raised to 4 by 32 multiplied by d by 2. And when you expand this, what you can see is you can actually take terms common outside, and this equation can be written as 8 WD divided by pi d cube 1 plus d by 2d. So tau total can be written as 8 WD divided by pi d cube 1 plus d by 2 times capital D. Now capital D, which is the coil diameter, and small d, which is the wire diameter, there is a ratio that is defined as C. C is capital D divided by small d. And this ratio is typically between 4 to 8. And this is a design parameter because you have spring coiling machines and they are designed, or the tools are designed so that you can have the different values of C. But typical values of C, which is the ratio of capital D to small d, is anywhere between 4 to 8. Now what we need to do is, we need to look at the design procedure for the spring. Now, the classic design procedure for spring is based on two parameters. One is the stress criterion. So for spring, we have to make sure that the spring is safe in shear. And then the second criteria is called the deflection criteria. You have to make sure that the spring is safe in deflection. So once these two criterions are met, we should be able to find out the design of a spring. So we can actually look at different parameters. But there is something else that usually goes on here. Now, this analysis, what is shown over here, is derived using plane equations. What it means is the equations are in 2 dimensions. But if you look at the spring is actually a 3D loaded structure. So what they do is they replace this guy by a factor K. So to account for 3D effects, because the load is actually going to be in 3 dimensions, K is called as Wahl's factor, and that is given as 4C minus 1 divided by 4C minus 4 plus 0.615 divided by C, where C is equal to capital D by small d. So there are 2 ways the spring can be designed. If nothing is given, you are welcome to use the equation that we just derived using the planar equation, 8WD divided by pi d cube multiplied by, in the parentheses, 1 plus small d divided by 2 times capital D. But if they ask us to use the 3D effects or consider the effect of curvature, this is also called a curvature effect, then we have to consider the Wahl's factor K, which is given as 4C minus 1 divided by 4C minus 4 plus 0.615 divided by C. So what this Wahl's factor is going to do is it's going to amplify the effect of stress. And I want you to just do this thought exercise. For a second, look at what this factor currently is. If I write this factor down, it is 1 divided by 1 divided by 2c. So what this is going to do is basically this factor is greater than 1, and it's going to amplify the effect of stresses. What Wahl's factor does, it makes this factor K much greater than 1. And that is how we take into account the effect of curvature and 3D loading conditions. So again, it depends upon what they are asking. If they ask that the spring design needs to be done using the curvature effects, spring design need to be loaded using the Wahl's factor, then you will use K is equal to 4C minus 1 divided by 4C minus 4 plus 0.615 by C equation. But at any rate, the value of C, which is the ratio of coil diameter divided by wire diameter, would be given to us, and that is what we will use. Okay, so let me give you the design of closed coil helical spring. Design of closed coil helical spring. Step 1, they may give you the value of design load, or they will give you the operating parameters. So they may say, hey, the spring is supposed to have a spring rate of 10 Newton per millimeter and the deflection is 10. So we know from the spring rate and the deflection, the total force is 100 Newtons. So it's totally depends upon the problem statement. The first thing is find maximum load W on the spring. Then the next thing is find out the torque that is applied on the spring. Find torque applied, and which is simple equation is W times D by 2. Please note the ratio C, which is capital D by D, will be given. If it is not given, we have to look at the design data book and find it out. The next thing is find the total stress on spring, and you can use either the Wahl equation or the regular equation. So you can find out tau total is equal to 8 WD divided by pi d cube 1 plus 1 divided by 2c. So this equation is when we neglect 3D forces and curvature effects. If they ask us that the curvature should be considered, so if curvature is to be considered, then K, which is the Wahl's factor, it's 4C minus 1, 4C minus 4 plus 0.615 divided by C, and tau total is equal to this factor K, 8 WD divided by pi dq. Now from this equation we should be able to find the diameter or wire diameter of spring. Now with this information we should be able to find out the coil diameter. Coil diameter is equal to C multiplied by the wire diameter. Then we should be able to find out the outside diameter, which is capital D times small d. We should be able to find the inside diameter, which is capital D minus small d. And the next step is to find out number of turns. Find number of turns. And to find number of turns, we have to look at the deflection. The deflection is given as delta is equal to 64 W R cube N divided by GD raised to 4. And this comes from the deflection equation in mechanics of material. So as you know, W is the load, R is equal to capital D divided by 2, G is equal to shear modulus or modulus of rigidity. This will be given to you, and D is the wire diameter, and N is equal to number of turns. So in this equation, typically delta value will be given to you. There are two ways this problem can be defined. Either they will give you the value of delta, they will give you the value of W, G will be known, R is already found out, D is found out, the only unknown is N. So all other dimensions are known, so you can find out the value of N. Alternatively, they can give you spring rate. So spring rate is by definition W by delta. So what you can do is you can rewrite this equation as 1 divided by spring rate is equal to 64. So 1 divided by spring rate is 1 W delta 64 R cube N divided by GD raised to 4. So there are two ways the problem can be specified. But no matter what is the setup, we have to find out the value of N. Once value of N is found out, we can find free length, and free length is given as LF is equal to N times D plus N minus 1 multiplied by 0.1 And this equation actually comes from the way the spring is coiled. So what I want to show you is, imagine that if the spring is coiled in a compact fashion. The spring is coiled in the compact fashion. You can notice that this is one diameter, this is other diameter, 3 diameter, and in between these diameters, these wires, you have small clearance. So this is that clearance, and depending upon the way the coils are compacted, you can have small clearance or you can have a large clearance. The last thing is nothing but the pitch of the coil. Is equal to usually delta plus typically it will be D. So if you think about it, the pitch from here to here, and this delta is nothing but the clearance. So delta is nothing but the clearance. If you want to find out the energy stored in spring, which is 1/2 W times delta. So if you look at the spring design, there are different types of springs. You can have helical spring, you can have spiral springs, you can have leaf springs, you can have Belleville springs, closed open coil, you can have tension springs, you can have compression springs. So first we are going to look at the design of helical spring, and the design procedure for helical spring is very straightforward. You have strength based design, wherein what you find out is the total stress, which is because of the direct shear and torsional shear. And the equation that we derive is based on the simple mechanics of material equations. But if you want to take into account the effect of curvature, then we have to consider something called as the Wahl's factor. The purpose of the Wahl's factor is sort of amplify the total effect of stress so that it correlates with the actual stress. And again, this is an empirical relationship. And then the procedure for spring design is starting with load determination, torque determination, finding out the total stress. So if they give you the spring material, typically spring steel, you will know the value of tau max or tau design, and you can find out the value of diameter of the spring and the capital D, which is the coil diameter and the wire diameter. With that information, you can find out the outside diameter and inside diameter. Moving on, you can find out the number of turns, and once you know the number of turns, you can find out the free length, you can find out the pitch of the coil, and you can find out the energy stored. Okay, now let me ask you, do you have any question? On the spring design, you can raise your hand or you can type the question in the chat window. If there are no questions, let me work out a problem. So design a helical spring max load is equal to 1000 Newton. the deflection is equal to 25 millimeter. The spring index is another name for C. Spring index, which is capital D by small d, is equal to 5. Tau is 420 Newton per millimeter square. And please note, this is spring steel. That's why the value of tau is quite high. Modulus of rigidity, which is G, is 84 10 to the power 3 Newton per millimeter square. And he's saying consider curvature effects. So whenever they say consider curvature effect, what we need to do is we need to consider the Wahl's factor. So Wahl factor is given as 4C minus 1, 4C minus 4, 0.615 divided by C. This equation, 4 times 5 minus 1, 4 times 5 minus 4, 0.615 divided by 5. So the Wahl's factor is going to be 1.34. Now, step 1, so design a wire diameter, which is D. Tau is equal to 8 WD divided by pi d cube times K, where K is the Wahl factor. And please note, tau value is given to us 428,000. Value of capital diameter D is 5 times the small diameter, because the spring index T divided by D is equal to 5 is given to us. Pi d cube multiplied by Wahl's factor. And once you solve this equation, the only unknown in this equation is the value of D, which is 7 millimeter. Once you know the wire diameter, you can find the coil diameter, which is C times D. You can find out the outside diameter, T plus D, which is 42 millimeters. You can find the inside diameter, which is capital D minus small d, which is 28 millimeter. Now next step is to find number of turns. Find number of turns. We use the equation delta is equal to 64 W R cube N divided by G T raised to 4. Delta is equal to 25 is equal to 64,000 35 by 2 cube multiplied by N divided by 84,000 multiplied by 7 to the power 4. Once you solve this, you will get value of n is equal to 15. Then to find free length, L is equal to n times d plus n minus 1 multiplied by, depending upon the clearance that we have, say 16 times 7 plus 15 times 1. So 15 times 7, 14, 1 plus clearance is 152 millimeter. And the pitch is equal to D plus clearance. So the diameter is 7, and I'm arbitrarily assuming the clearance to be 2 millimeter. So 9 millimeter is the pitch. So assume. Okay, this is how you will design a simple spring. Any questions in spring design? So let me take the design problem for clutch spring. So now at this point, what I want to do is I want to introduce you to the concept of clutch. And some of you may know the concept of clutch, but here is the idea. You have an engine, and this engine, or an electric motor for that matter, is connected to a transmission. So this is the transmission. So let's consider this is an engine, some sort of prime mover, and this is connected to a transmission. Now when we start the engine, momentarily when the engine is being started, transmission is disconnected from the engine. So when we start, so engine is started in no load condition. Engine started in no load condition. So what it means is momentarily when we start the engine, what we do is we put the car or the transmission in neutral, and in neutral the transmission is actually declutched. In other words, the transmission is separated from engine. And when the engine starts running, picks up speed, at slow speed, what we do is we connect these two shafts together and we align those. And then the power transmission from engine to the transmission can start. So this is power transmission. And the way the clutch works is by means of friction. So what happens is, in clutch, you have something called as a clutch plate. And I'm going to show you a very simple example of a clutch plate. So you have a plate on the driver's side and you have a plate on the driven side. So what you have is So you have a plate, a clutch plate on the driven side. This is the driven side. And you have a clutch plate on the driving side. This is the drive side. And there is a teeny tiny gap between these two plates. Now, when you have this gap, the drive is decoupled or declutched from the driven system. So this could be a fan, this could be a generator, this could be a fan, or this could be a transmission, or this could be some sort of a prime mover. So there is a gap and the drive can be started. But what clutch does, when you want to clutch these two together, that means the drive plate should come in contact with the driven plate. And the way it happens is you apply forces. You continuously apply force on this plate. So this is called as the clutch plate. Clutch plate. What you do is you apply the force on the clutch plate in such a way that these two plates, they come in contact. And there is frictional surface in the clutch. So initially the clutch may slip. After it comes into the complete contact, the clutch remains as is, and this gap is actually zero. And then the power from the drive side is transmitted onto the driven side. So the way clutch works is, I want to show you sort of a three-dimensional view of how this clutch system works. So you have a shaft, and this shaft is actually splined. So this is a spline shaft. This is a spline shaft. And on the spline shaft, you have a plate, which again is also splined. And this plate is allowed to slide back and forth by a teeny tiny amount. This plate is allowed to slide back and forth by a teeny tiny amount. And on here, there is another shaft, and I'm going to show you a very rough sketch. So this is a very crude sketch. The real life clutches are much complicated. So if you look at it, so this is drive, this is driven, and this is solid shaft, by the way. This is driven, and this is connected to the prime mover. This is connected to prime mover, so engine, and maybe a generator. And now visualize that on this spline, there is some sort of a bracket. So you have a bracket, and this bracket rotates along with it. And here, there are springs. So this bracket is attached to this shaft, and in between this bracket, I'm gonna show this bracket like a rigid bracket, a rigid plate, a bracket attached to shaft and does not slide. This clutch plate slides. So what you have is, in between this rigid plate and the plate that is allowed to slide forward and backward, you have springs. And then you could have some sort of a lever mechanism over here that can be used to push the springs or push the plate against the springs. So what will happen is you can selectively, this is the lever, and this is actually basically this becomes a clutch lever. So if you look at your car, this is connected to the pedal. So once you press the pedal, what happens is the plate, the clutch plate is moved away from the corresponding mating plate and the power transmission is stopped. But otherwise, if you release the clutch lever, then the plate comes in contact and the engine, the power transmission can go from engine to driven shaft. The fundamental principle of power transmission because of the clutching is due to friction. So this is friction. You could have a single plate clutch. You could have a multi-plate clutch. Multi-plate clutch gives you more surface areas, and the equation for power transmission is the same as what we saw a moment ago. Mu times Rm is nothing but the torque that is transmitted by the clutch. So clutch has multiplied by W. This is W. W times Rm divided by 2. Actually, if you use Rm, we don't use half. So this is mu times W times Rm. So you have mu times W times Rm. That is the torque that is transmitted by the clutch. And you will notice for continuous power transmission, the torque transmission capacity of the clutch should be greater than the torque that needs to be transmitted. Otherwise, what would happen is the clutch would slip. And that could happen in the manual cars. When the clutch gets old, its power transmission capability drops down. In other words, the friction surface. So the clutch is going to have friction surface here and friction surface here. So deliberately, they add a frictional surface on the mating surface. So the friction drops down. So when the friction drops down, power transmission capability of clutch drops down, and then the clutch starts slipping. So it stops, or the power transmission capability of the clutch is reduced. So main thing here is you also have springs over here. So these are the springs for the clutch plate. So the purpose of the springs for the clutch plate is continuously apply the force, which is W, so that the power can be transmitted. So let's take an example where we are designing the springs for the clutch. So next problem. Power is transmitted by single plate clutch and the axial thrust is provided by 8 springs. The total force is equal to 2400 newtons. Determine wire dia based on following information. Compression of each spring, is equal to 25 millimeter. spring index (8), tau design is 400 Newton per millimeter square, and G, which is the shear modulus, is 84,000 Newton per millimeter square. And to be on the safer side, we will consider curvature effects. So if we consider the curvature effects, we have to find out the Wahl's factor, which is 4c minus 1, 4c minus 4, 0.615 divided by c. And once you substitute the value of c as 8, the Wahl's factor is 1.18. Then tau is equal to 8 WD divided by pi d cube times k. Now what I'm going to do is I'm going to substitute the values 400, 8. Now there are 8 springs. The total load is 2400. So load per spring, this is the load per spring, multiplied by 8 times d divided by pi d cube 1.18. That gives me diameter is equal to 5 millimeter. Now with this, I should be able to find out the inside diameter, outside diameter. So DO, outside diameter, which is 8 times 5 plus 5, 45. DI, inside diameter, 40 minus 5, 35. To find number of turns, delta is equal to 64 W R cube N divided by G D raised to 4, 25, 64, W is 2400 divided by 8 times R. N. So please note D is equal to C times small d. This is the wire diameter. Small d is the wire diameter, which is 8 times 5. So capital D is 40. So R, which is capital D, this is the coil diameter. This is the wire diameter. D divided by 2 is 20. 5 to the power 4. So N is equal to 9. So this is how you will design the spring for a clutch application. And design of clutch is actually also very straightforward, but when we get a chance later, we can talk about design of clutches. Again, design of clutches is based on the condition for friction. Let me take design procedure for one more type of spring, which is called as the flat spring or leaf spring. So leaf springs are used in a lot of applications. Typically, when the load is higher, the leaf springs are used. And let me explain the design procedure for leaf spring. The helical springs are based on the torsion principles. The leaf springs are based on the bending. So let me give you the design process for design of leaf spring. And there are two procedures given in the textbook. You can follow any procedure. So leaf springs, they look something like this. And if you look at the springs that are usually on the rear side of the truck or the heavy vehicles, you will notice the leaf springs something like this. So you have a couple of full leaves, then you have partial leaves, and these leaves are held together in place using some sort of a center bolt. And then you have recoil clips that help control the recoil. And then you will notice that usually they are mounted somehow attached to the axle, and this side is attached to the chassis. So this is the leaf spring. So step one, determine strength of each leaf. And that is given from the bending equation. Where F is the stress. So stress, I is the moment of inertia, and Y is the distance from neutral axis. Usually the leaves have rectangular cross section, and typically what they have is they have B to T ratio. So if this is the thickness and if this is the width, W by T ratio is fixed, and that is given in the design data book. So what we do is we substitute the design stress. This is the design value. Then the selected W by T ratio and find out the strength of each leaf. The next step is we determine number of leaves, which is we look at the loading condition, find out the maximum bending moment, and divide that by the M, which is the moment capacity we got from step one. Next step is we find out the radius of curvature. And the equation for radius of curvature comes from m divided by I is equal to F upon Y is equal to E divided by R. This is the fundamental equation for bending. R is equal to E I divided by M. The next is calculate the deflection at the center of the spring, which is given as delta is equal to L square divided by 8R, where L is the length of the spring. So if you look at the leaf spring, this actually is the length, and R is the radius of curvature that we just found out from step 3. So with this, we should be able to design the leaf spring. There is another procedure that can be used. It's first we determine B by T ratio or W by T ratio for each leaf. Then we find effective length which is L minus central band width, and this central band is used to keep those leaves together. Then what we do is we use maximum bending stress on the full length leaf to and equate that to the safe bending stress. So we consider the max bending stress on full length leaf and equate it to safe stress. So for example, if it's a simply supported beam, you will have capital M is equal to W times L by 4. This is the maximum bending moment. And then you can find out sigma B is equal to, that equation is 18M divided by W T square 2NG plus 3NF, where NG is the graduated leaves. So number of graduated leaves. The graduated leaves means the smaller leaves, not full length. And NF is number of full length leaves. And once you do that, the last step is find value of W as W by T ratio is known. This process may seem convoluted, but once we work out a problem or two, you will realize that this process is fairly straightforward. And just like any other design process, that you will have to go back and forth and make corrections so that your design is safe. Okay, in today's class, we looked at power screw design, we looked at spring design, we looked at helical spring, and we looked at design of flat springs, or leaf springs. So I'm gonna stop here today. If you have any questions, I would be happy to answer.